A human playing the role of a robot, the reversal of the old dream of machines imitating man. This excerpt is from a Swiss television show. Robots are in fashion, and time again, they're directly compared to human beings.
In the year 3000, the question will be, what's for dinner?
Advertising shows the trend. A sexy robot is the symbol of the brave new world in a TV commercial for canned food, visualized with state-of-the-art computer graphics.
To Jupiter and back and back and back. Even in the year 3000, we see the brilliance of food in cans.
Even the automotive industry, as the largest user of industrial robots, uses attractive metal ladies to sell its products. The artistic portrayal, even of industrial robots, knows no limits. Another advertising example, the four-armed monster with man-like features, symbol of the new technology, the high-tech world. The dream of man-like machines is old. At the end of the 18th century, the clockmaker's craft made it possible to build mechanical dolls which could be programmed to perform complex movements. After visiting the Swiss clockmaker Jacques Dreux, the creator of these androids, Mary Shelley was inspired to write the novel Frankenstein, a good example of the frightful and tragic side of progress. The term robot, as a man-like machine, first appeared in the play R.U.R., Rossum's Universal Robots by the Czechoslovakian writer Čapek. Man-machines are part of many science fiction movies. Robots as film stars, along with other monsters such as Godzilla and King Kong. The toy industry copied the film robots a millionfold in tin and plastic. Today they're sought after collector's items. The descendants of these mechanical toys are electronic devices which can be programmed to move their arms, pick up objects, and follow predetermined paths. To call this Japanese toy home robot might be a bit of an exaggeration, but over 50,000 of them have been sold. The charm and excitement of automatons is one side, the threat the other. It too is audience effective. It was a main theme in Fritz Lang's film Metropolis and Charlie Chaplin's Modern Times. Inhuman machines and machinery which destroy individuality. And still today, many people think of the industrial robot as dangerous, as a symbol of the machine, the job killer. Or is it a beneficial reformer, improving the quality of working life? What lies behind these cliches? What part does the robot and what part does the industrial robot play in the factory? especially in the new factory. What does a modern factory really look like? The robot as a man-machine is still science fiction. Today, there are different automatic machines for a wide variety of applications. But robots are always part of the other, somewhat less spectacular components of rationalization. For example, special purpose machines, like this vibrating conveyor feeding parts for assembly. Automatic dedicated machines. Computer-controlled machine tools. Flexible manufacturing cells. Robo-vans. Only through the combination of mechanics and electronics, the Japanese coined the term mechatronics, was it possible to achieve this technological breakthrough. The Fraunhofer Institute in Stuttgart is internationally renowned for its accomplishments in robot technology. 25 years ago, they began research and development in the field of flexible automation. Today, every industrial operation, regardless of its size, has to meet 4 requirements. First, quality. A company must ensure a constantly high product quality. Second, cost efficiency. The products have to be produced economically. Third, flexibility. The industry must be able to adapt to fast changes in market demand. And fourth, improving the quality of work life. The need to create more humane workplaces. Flexible automation can be the key to meet these requirements. These elements of automation, if applied correctly, are crucial for the economic success and sometimes even for the survival of an industrial enterprise. Here are some practical examples. Artificial hip joints are extremely delicate, especially with regard to durability and security against fracture. Quality assurance already starts in the design phase. The finite element method is an engineering procedure. It enables the designer to analyze stresses in the workpiece even before manufacturing has started. An industrial robot is handling a workpiece. Later on, it will take it to an inspection station while another workpiece is being processed. An example of what is known as in-process quality control. Constant quality is essential. The notorious Monday products are things of the past. The screw in this video recorder is always tightened with the same torque, 7,500 times a day, and not one screw is left out. High productivity is closely related to cost-efficient manufacturing. A good example is the assembly of these Swiss quartz watch movements on an automatic dedicated swivel table. Flexibility is not the issue here. The automation is non-programmable and fixed, the only way to meet the competition from the Far East. Manual labor has been reduced by 2/3 compared with the old assembly line. Fortunately, no job losses occurred, since the machines for the new line are produced in-house and require manual workers. Keeping a small inventory helps reduce high costs tied up in floor space, transportation, and inventory capital. This dishwasher assembly line uses a new method called just-in-time production. The dishwasher parts are manufactured right at the line. A warehouse is unnecessary. Part transportation is kept to a minimum. In the just-in-time production, suppliers have to deliver the required parts to the right place at the right time. However, should it be necessary to keep parts in stock, the warehouse itself can be automated. This unmanned warehouse is managed by computer. The computer controls the material handling and the transportation by means of unmanned electro-vehicles. These robo-vans or carriers are often part of flexible automation systems. Personnel costs can be saved. Machines replace manual labor. But that is not all. The new machines can work without interruptions, overnight, or over the weekend, provided that enough raw material is on hand. Nonetheless, this type of production requires high capital investments, as well as operating and maintenance costs. Flexibility might be the most important demand on the new factory. Mass production, using, for this purpose, specifically designed machines, has one disadvantage. It takes a lot of time and money to adjust the machines to a new product. Usually, the system has to be changed mechanically or has to be replaced by an entirely new system. Flexible automation, however, makes it possible to reach both goals at once: productivity and flexibility. Flexible manufacturing cells serve as an example. They're a combination of industrial robots and computer-controlled machine tools, the CNC machines. A CNC machine can process different workpieces automatically, in this case, turbine buckets. New computer programs can easily change the sequence of operation. In addition, the machine is equipped with different tools which can be changed automatically if necessary. An automatic system for changing workpieces replaces manual labor. Here, an industrial robot loads and unloads the machine. On a larger scale, the cell is called a flexible manufacturing system, where several workstations are linked in a flexible way to process different workpieces passing through the system. There are several other computer applications which increase flexibility. One of them is CAD, Computer-Aided Design. This is a relatively old but effective electronic aid which can drastically shorten the design and product development phase. Shortening the design process allows for fast reactions to meet rapidly changing market demands. Process planning is part of information management. It determines how many parts are to be manufactured, when, where, by whom, and with what tools. Another part of information management is operating data management, which processes all data collected on the shop floor. The fourth demand on the new factory requires the improvement of the quality of work life. Automation may help to reduce physical and psychological stress. Industrial robots take on the task of handling heavy parts or work in hazardous and unhealthy environments. or simple and repetitive tasks, the classic assembly line jobs poignantly copied by Charlie Chaplin in his film Modern Times. An example for the new generation of assembly line workers are these three robots putting together fuses for telephone systems. But automation may not always imply the improvement of the quality of work. The remaining work can be simple, repetitive, and monotonous tasks, directly exposed to the brutal machine cycle. That the technical components necessary in the new factory already exist and are in operation, but usually as isolated islands of automation. These isolated islands of automation, although flexible, do not make up the new factory. Their common denominator are electronics and microelectronics. They make it possible to link every automation component to a data network, the backbone of the new factory. Every process from order entry through product design and manufacturing to the final shipment can be expressed as data and used for control and monitoring purposes. Thus, the islands of automation can be linked to an integrated system through a common database. The new key word for this highest form of the so-called C technologies is SIM, short for Computer Integrated Manufacturing. SIM means more than hooking up separate machines to a manufacturing system. SIM is the integration of all factory functions at every stage. Such functions as design and development, operation scheduling and planning, as well as manufacturing, including assembly and quality control. Yet integration is not complete until the administration, marketing, distribution, and business planning functions have been incorporated into the system. Using computers, such a flexibly automated factory is able to manufacture products in small quantities that meet the market requirements while maintaining a productivity only equaled by mass production. Thus, manufacturing, once labor-intensive, then capital-intensive, is becoming more and more data-intensive. Nonetheless, the time is yet to come. SIM has only been introduced in a handful of factories, and so far only partially. However, just analyzing the introduction of a flexible automation system can lead to important insights. Steve Miller at the Carnegie Mellon University in Pittsburgh.
In some ways, the state-of-the-art automation in the middle of the 1980s is sending people back to square one to think about, what am I doing? Why am I doing it? How am I doing it? And the reason they're asking these questions is that in order to do these same kinds of tasks with machines, everything must be explicit. Everything must be written down. Everything must be in a way where it can be described or modeled in some kind of way that it can be embodied in software. And we are finding out that as people try and apply advanced computer-based decisions to certain kinds of managerial decision-making, or apply advanced robotics to certain kinds of materials processing, that they fundamentally don't understand the basic task going on. So on one hand, they're trying to develop the new technology, and on the other hand, they're trying to understand manufacturing.
During the course of the series, international examples will demonstrate how flexible automation systems have been realized. For one, the introduction of an automated assembly system for telephone receivers in a medium-sized Swiss company. The third program deals with an industrial robot pioneer. Leif Jonsson, owner of a tiny company in Sweden, bought his first robot in 1974, at a time when the user himself had to adjust the robot to the specific task. The question is, how can a small company at a reasonable cost automate with robots? A dishwasher plant in Louisville, Kentucky presents a sharp contrast to the small Swedish family business. With 1,500 employees and automation moving in the direction of SIM, the factory produces 10 dishwashers a minute. 10 years ago, the company was on the verge of closing. But thanks to well-planned automation, it has regained its market leadership. A factory of similar proportions produces video recorders in Japan. The 150-meter-long assembly line for the motor unit of the recorder is the subject of the 5th episode. The product was specifically designed to facilitate automated assembly, using only a few robots. A medium-sized company in southern Germany manufactures highly sophisticated plate-working machines. In our case, a manual workstation was automated to process a very diversified spectrum of different parts. An example of the high degree of flexibility which can be economically achieved with industrial robots. The 7th program deals with the social consequences of industrial automation, using examples from the factories portrayed in the previous episodes. Changes in the workplace, job loss, education, training, retraining, and stress are some of the issues. The last part of the series is devoted to the future of automation. An American steam turbine manufacturer has made SIM a reality, from order entry to shipment of the product and beyond. Hard to believe that one of the old Thomas Alva Edison buildings was to become one of the first computer-integrated manufacturing facilities in the world. And finally, what will happen after SIM? What part will artificial intelligence play in the factory of the future?